This lecture is part of an undergraduate course on complex analysis and will be about elliptic functions. So first of all, what is an elliptic function? Well, they have almost nothing to do with ellipses. They're called elliptic functions for a long, roundabout historical reason vaguely related to the function that gives you the arc length of an ellipse, but it's best to forget about ellipses. What they really are doubly periodic functions. So you recall that for the reals we've got singly periodic functions which say satisfy f of x plus 2 pi equals f of x, and there are lots and lots of interesting such functions. We can have sine nx or cosine nx for any integer n, and there's a whole theory of Fourier series about decomposing functions like this. If we're looking at complex rather than real analysis, things get twice as exciting because a function can have two periods. So these periods are traditionally called omega 1 and omega 2. And you can sort of draw a picture of this. So suppose we take the complex plane with a point 0, and we might have a point omega 2 here and a point omega 1 somewhere down here. And now, just as if a function has period 2 pi, it also has period 4 pi and 6 pi and so on. If a function has periods omega 1 and omega 2, then it also has periods that are any integer linear combination of these. So if you draw a sort of rectangular, a sort of grid like this, not necessarily rectangular, these are sort of diamond shapes or something, then all of these points here are also periods. You also see that any complex number is equivalent to some number in this region here by adding a multiple of omega 1 and omega 2 to f. So this region here is called a fundamental domain. Actually, the definition of fundamental domain is slightly vague because I haven't said whether the boundary points are in the fundamental domain or not, and I'm not going to bother saying this because it's a bit of a mess trying to work it out. So the first question about elliptic functions is, are there any? Well, if you just allow any functions, it's obvious there are, but we can ask, are there any holomorphic elliptic functions? Well, obviously there are constants, but are there any other than that? And the answer is no. If f is holomorphic and elliptic, this implies f is constant. And this follows fairly easily because f is bounded in a fundamental domain, and that's because the fundamental domain is compact, at least if you include all the boundary points, and f is continuous, and you know that a continuous function on a compact set is bounded from real analysis, I guess. So f is bounded on the whole of the complex plane by periodicity. See, it's bounded in the fundamental domain, and its value anywhere else is equal to its value in the fundamental domain. And if it's bounded and holomorphic, we know that f is constant by Liouville's theorem. There's not much to say about holomorphic elliptic functions, and instead we should look at meromorphic elliptic functions and ask if there are any. And you remember meromorphic means it's allowed to have poles, and that's okay because, as we said, poles are almost as nice as being holomorphic. So what we want to do is to find a meromorphic function such that f of m omega 1 plus n omega 2 plus z is equal to f of z for all m and n that are integers. And what we notice here is that we have a group of translations of the complex number, and this group is isomorphic to the sum of two copies of z. And if we've got any group, there's a very simple way of making functions invariant under the group, which is to take an average of a function. So we can just take f of z to be the average of g of z. And this average just means we sum over all m and n of g of z plus m omega 1 plus n omega 2. So this obviously gives an elliptic function, right? Well, not quite so fast. There's a slight problem. F is elliptic if the series is absolutely convergent. So obviously if the series isn't convergent, then this isn't going to make sense, and we can ask, should it be just convergent or absolutely convergent? Well, the trouble is, if you talk about it being convergent, you've got to really worry about the order you sum these terms up in, and that's a real pain. So it's much easier to insist that this series should be absolutely convergent, then we don't need to worry about order, and this is obviously doubly periodic. So what we've got to do now is investigate when this series is absolutely convergent. So we've got this function g of z, and we're looking at all the values g of z plus omega 1 m plus omega 2 n. So let's draw them all. Well, we've got a point z here, and here we've got z plus omega 1, and here we've got z plus omega 2, and we get a whole lot of other points lying on a sort of lattice like this. And let's assume that g of z is less than or equal to some constant over z to the alpha for z large-ish, for z sufficiently large. And now we're going to try and estimate this sum, and what we do is, well, we've got to estimate the sum over all these points, and what we're going to do is we're going to estimate the sum of the points in some sort of ring-shaped region. So suppose this distance here is a, and this distance here is a plus 1 for some integer a. Then the number of points of the form m omega 1 plus n omega 2 in the ring between these things is going to be less than or equal to some sort of constant times a, because you can sort of see this, the length of this ring is going to be about a, and these points are sort of uniformly distributed. So the sum will be bounded by, we want to sum over all a being 1, 2, 3 and so on, and then we take some constant times a, which is the number of points in this ring, divided by divided by a to the alpha, because a to the alpha is an upper bound for g for all the points here. So we want to know, when does this converge? And this converges if alpha is greater than 2. Because if alpha is equal to 2, this is just the harmonic series, 1 plus a half plus a third and so on. And if alpha is greater than 2, you know from real analysis that that series converges. So this is the key condition we've got. We need that g of z should decrease more quickly than z to the minus 2, except maybe near the origin. So this now gives us lots of examples of elliptic functions. So what we can do is take g to be any rational function of degree at most -3. So this is less than -2, so it makes the series converge absolutely, which is fine. That's what we want. So for example, we could take g of z to be 1 over z minus a times 1 over z minus b times 1 over z minus c for any a, b and c, and this would then do. So this would then have poles at a, b and c, and it would not only have poles at a, b and c, but it would also have poles at a, b and c plus m times omega 1 plus n times omega 2. So we can find lots of rational functions with at least 3 poles in a fundamental domain. Well, this leads to the obvious question: can we find some sort of elliptic function f with 1 or 2 poles in a fundamental domain? And there's a more general question. You notice that an elliptic function f is determined by its zeros and poles. And that's because if f1 over f1 and f2 are elliptic, then f1 and f2 has no poles, so it must be constant. So when I say it's determined by zeros and poles, I mean up to multiplication by some constant. So this means we can specify elliptic functions by just giving their zeros and poles, provided we know which selections of zeros and poles give rise to elliptic functions. So in particular, we could ask, if we take 1 pole and some zeros, can we find an elliptic function with that as a pole? And in order to answer that, we're going to use the argument principle. So the argument principle states the following. So suppose f is some meromorphic function. And it's going to be meromorphic in some region u, and we want to know how many zeros and poles it has in u. And what we do is we look at the function f prime of z over f of z, which looks like a sort of funny function to consider. I'll explain where this comes from in a moment. But in the meantime, if we look at f of z equals, and suppose it looks like a n z to the n and so on at 0 or at some point, then f prime of z looks like n a n z to the n minus 1 plus something. So f prime of z over f of z is equal to n z to the minus 1 plus higher terms. And you can see this has a residue equals n, which is the order of 0 of f at 0. And the order of a pole sort of counts as minus the order of the 0. So this is minus the order of a pole if it has a pole. So poles should be counted as zeros of negative order. So the residue of this at 0 is just the order of the 0 at 0. And similarly, the residue of this at any point A is just the order of the 0 at A. So we see that the integral over C, that's this contour, of f prime of z over f of z dz, when multiplied by 1 over 2 pi I, is equal to the number of zeros minus the number of poles of f. And this is the argument principle discovered by Cauchy. And you may say, why is it called the argument principle, since you don't seem to be arguing about anything? Well, the answer is argument actually refers to the change in argument of f of z. So the argument of f of z is, of course, just the angle it forms with the origin. And why is this? Well, it actually should be 1 over 2 pi times that. Well, that's because we can carry out this integral by writing down an explicit integral of that. And that turns out to be easy because this is just the derivative of log of f of z. And you may think this is a bit fishy because you've got to be a little bit careful. Log of fc is multi-valued. It can change by a constant when you go round something. But that doesn't matter because we're taking the derivative which kills off this arbitrary constant. But anyway, it means this integral here is 1 over 2 pi I times the change in log of f of z as you go once round this contour. And when you go around this contour, f of z doesn't change, but log of fc does change because its imaginary part is more or less just the argument of f. So 1 over 2 pi I times the change in log of fc is equal to 1 over 2 pi times the change in the argument of f. And that's why it's called the argument principle. You can count the number of zeros in a region just by examining how the argument of f changes as you go round it and dividing by 2 pi. Of course, you've got to be a little bit careful if there's a zero exactly on the boundary, but we won't worry about that, at least not very much. So let's now apply this to elliptic functions. We can ask, suppose f is elliptic, how many zeros and poles does it have in a fundamental domain? So let's apply the argument principle to this. So here's a fundamental domain. Here's 0, omega 1 and omega 2. And the number of zeros minus the number of poles, this is in the fundamental domain, this is of f, is equal to 1 over 2 pi I times the integral over c of f prime of z over f of z dz. Well, that doesn't seem to be much use because not only is this a rather messy looking thing to try and integrate, but we don't even know what f actually is. So how can we possibly figure out this integral? Well, it turns out to be really easy. So here we've got this contour c, which kind of goes around like this. And let's have a look at these two bits. Well, on these two bits, f is the same because it's periodic. F of z plus omega 1 is equal to f of z. So in one integral, we're sort of integrating in that direction, and the other integral, we're integrating in the other direction. So the integrals cancel. And it shouldn't take you too much effort to realise the integrals here and here also cancel because this time f has period omega 2. So the fact that f is doubly periodic implies that all the integrals just cancel out and this is just equal to 0. So we have this basic fact about elliptic functions. The number of zeros is equal to the number of poles. And of course we count the number of zeros and the number of poles in a fundamental domain. And you may say, what happens if it has a zero or a pole on the boundary of a fundamental domain? Well, that doesn't really matter much. If it's got a zero here, we would just sort of go round it like this. And again, the integrals will cancel out. So zeros and poles on the boundary, you should only count them as being sort of half in the fundamental domain, because if we've got a zero here and here, we don't want to count that as 2 zeros in the fundamental domain, we just want to count it as 1. And you have to be equally careful about zeros at one of these corners. You just have to be a little bit careful to count the number correctly and not overcount. So next, we can push this idea a little bit further, because suppose we look at 1 over 2 pi I times the integral of f prime of z over f of z times g of z dz. Well, again, we can work out this using the residue calculus, and it's the sum over all zeros and poles of np, which is the residue of f prime over f, times g of p. So this is the residue of f prime over f. And this is provided g is holomorphic. If g is not holomorphic, you have to take problems with poles of g into consideration. So that's the residue of f prime over f, and this whole thing here is just the residue of f prime over f times g at each point p, or rho. And now we're going to apply this when f is elliptic. And what we're going to do is we're just going to integrate 1 over 2 pi I times f prime of z over f of z, and this time we're going to multiply it by z. And let's have a look what we get. Well, we get a fundamental domain. And now, if we try and cancel out the integrals over here and here, it doesn't work because f prime over f is the same, but z changes. So what does actually happen? So let's try and do these two integrals here. So we have an integral from omega 1 to omega 1 plus omega 2, and we subtract the integral from 0 to omega 2. And if we do this, remembering to put in the 2 pi I factor, we get the integral from 0 to omega 1 of f prime of z over f of z of, well, here we're going to get z plus omega 2, z plus omega 1 coming from this integral, minus c coming from the other integral. So here we get that one, here we get this term. And this is equal to omega 1 times the integral times 1 over 2 pi I times the integral from 0 to omega 1 of log of f of z dz. So here we've got the omega 1 there, and now we've just got to integrate log of f of z. And how do we do that? Well, f of z is periodic with period omega 1. Let's switch these, omega 1 and omega 2. No, I had it the right way around the first time. And that should, it's that one that should be an omega 2, sorry. So this integral here is just equal to the change of argument of f of z. So this bit is actually an integer because it's how much the argument of f changes as we go from there to there. So the sum of these two integrals isn't 0, but it's an integer times omega 1. And similarly, the sum of these two integrals is just an integer times whatever the other omega was, omega 2. So, so what we find is the following result: the sum over all zeros and poles of p times np is equal to m omega 1 plus n omega 2 for some m and n that are integers. So here we've got another non-trivial relation the zeros and poles have to satisfy. And now let's show that f cannot have exactly one pole. Well, suppose that it has a pole at A and a 0, it must then have a 0 at B for some number B. Well, then we see from this that the sum of all the zeros minus the sum of all the poles must be m omega 1 plus n omega 2 for some m and n. That's in here. But that means it also that well if it's got if A and B differ by m omega 1 and n omega 2, and if it's got a 0 at B, then it must have a 0 at A by periodicity. But we've just said it's got a pole at A, so this gives a contradiction. So, so an elliptic function can't have exactly one pole in the fundamental domain. So what we've shown is that we can find elliptic functions with 3 or more poles in a fundamental domain, and we can't find an elliptic function with one pole in a fundamental domain. So we have the following question: what about 2 poles in a fundamental domain. More generally, we found two conditions that the zeros and poles have to satisfy. So the sum of np must be equal to 0, and the sum of p times np must be equal to m omega 1 plus n omega 2 for some m and n that are integers. And we can ask, are there any other conditions that the zeros and poles have to satisfy in order to satisfy this condition? So what we're going to show soon is that these are sufficient conditions for an elliptic function. And we're also going to look at the borderline case and show that you can find elliptic functions with exactly two poles. So you remember when we were looking at convergence of a sum of a rational function, it converged for things of degree less than -2, but -2 is a sort of borderline case where it diverged but only just diverged. And when a series only just diverges, you can sometimes sort of make it converge by twiddling it very slightly. And that's what we're going to do next lecture in order to find the Weierstrass elliptic function.